Yeah, today we're going to start with the last topic of rigid body kinetics, which is to study how the impulse momentum equations work for rigid bodies. So we did this kind of separately for particles, and most of it is really not changing much with respect to what we learned with particles. But we're going to see what is it that we need to be aware of and some of the key things that we need to have in mind. All right, so everything in kinetics that we normally do, or not that we normally do, everything in kinetics is based on this: Newton and Euler equations, right? So, Euler equation is just a consequence of Newton's second law. And we have discussed many times that when we have rigid bodies, and we are considering linear motion or translation, which comes from the acceleration, we need to deal with the center of gravity of the rigid body, right? That's the big thing to remember. And this is also going to be valid when we study linear impulse momentum of rigid bodies. So we cannot calculate the linear impulse momentum of an arbitrary point. It needs to be, we need to use the center of gravity. Very, very important, all right? Now, for angular impulse momentum, we do have choices, and it's similar to what we had in, excuse me, in the Euler equation, that we could, make some choices about it. So we're going to review a little bit about it and learn how these two are calculated. And those are the objectives of this lecture, to introduce these two concepts for rigid bodies. And I'm going to, if I have time, I'm going to show a little bit more on how to use this kinetics table and how can it help in your study. So going into the material, we have discussed this a few times, right? Newton's second law takes many forms, but it's always expressing the same information. And here what we're saying is, look, let me separate Newton's second law, or let me just say, okay, I have a derivative of the velocity with respect to time. I send the differential of time to the left and integrate, right? And if we do that, what do we get? We get the linear momentum equation. We did that for particles. We can do it for rigid bodies. Now, as I mentioned, the key is that we cannot take any velocity to calculate the linear impulse momentum. We need to use the velocity of the center of gravity. Okay? So please, in the exam, remember this. Yeah, there it was. Now, for the angular impulse momentum, as I said, we have several choices, right? And we're going to make the choices that make our life easier, as we did with when we were calculating or using moments to in Euler's equation. And the choices are actually quite similar in the sense of what simplifies our lives. So let's take a look at this. Okay, so actually I should go over this a little bit. So when we were calculating the angular momentum of a particle, we were essentially taking this term, right? we were saying, okay, this particle, I can take the momentum about a certain point, and then I was crossing the velocity times the mass, which is the linear momentum of that particle, with the distance to the point that I wanted. Now, rigid bodies, we can also use that to calculate their momentum about an arbitrary point A, but because the rigid body can rotate, itself can rotate, then we also have to add its, for want of a better description, its intrinsic momentum. So that's what you have when you rotate. You remember when I was, fooling myself on the chair and trying to show you how by moving my arms I could stop myself. Well, this is kind of that hg. And we're going to see, how to calculate it. In essence, the momentum about the intrinsic momentum is nothing else than the moment of inertia about g, if we're calculating in about g, times the angular velocity that we have. And of course, you know that the momentum equation is giving you a change between two instances. So if our angular velocity has changed, then our angular momentum also changes. Is there any other way in which we can change our angular momentum? Looking at this equation here. Let's say from this state to this state. Is there anything that can change? What?
Shape changes or the distribution of mass changes, so the moment.
Exactly. So again, think about the skater that is jumping and opening arms, etc. You're changing the distribution of your mass, which means that your moment of inertia is changing. So changes in moment of inertia can also lead to changes in angular momentum, all right? In fact, yeah. So these are things to remember. Now, as we are engineers, we want to optimize our lives. Well, at least this is the way I think. I'm always optimizing everything. I want to, calculate this without this second term. I want to calculate the momentum, the angular momentum, without that second term. So we have a few good choices to do that, right? So if we see that we're calculating the momentum from an arbitrary point A to the center of gravity, and we see that this second term here, we want to get rid of it. Of course, we can say, okay, if I calculate the angular momentum about g, then I can get rid of that second term, right? Because the distance from the point of calculation is 0. So center of gravity, if you are in doubts of which point to use, that is the one that you should choose. Because you can always find the moment of inertia of your rigid body about the center of gravity. Now, if you do that, of course, this second term is eliminated. But then what we need to remember is that if I calculate my momentum there, I need to calculate my moment of inertia with g, right? That's very important, that we need to be consistent there with where we take moments and where we calculate our momentum about, or moment of inertia. Now, another good way of eliminating that second term is, of course, if we have if we take our arbitrary point to be, what other good choice we had for Euler equation? That is the third good choice, an easier one. A fixed point, right? If we use a fixed point for calculating our angular momentum, then the velocity of that point is going to be 0. And then, but then here you need to use the momentum it's going to be about a certain, about that point, the angular momentum that you're getting. So you're not really getting the angular momentum of the center of gravity, but you're getting the angular momentum measured from a fixed point of a certain rigid body, right? And then the last is the special point, C, in which the velocity, for instance, that the velocity of that point is 0, such that we get this cross product to be 0. And that is, of course, I use C because typically with no slip condition, we have a certain point that fulfills this. So essentially, it's like a fixed point, but it's not really a fixed point, right? Because we know that in our no slip condition, we don't really have a fixed point. Now, so these are the good choices. Now, there is something to remember. In the no slip condition, point C has 0 velocity if the surface is stationary, all right? So this is always, never forget this, because this is, can lead to some problems. And if the surface is moving, then this is not a good point anymore, all right? Any questions there? So things to remember, sorry. Linear impulse momentum needs to be about G. Angular impulse momentum of a body can be about, a point, any point that is convenient for us. And we follow these choices here to calculate. So I want to go to this problem that we did last time. Hopefully you remember it. And it was about calculating the work done from this disk when it was moving from position 1 to position 2, right? And then we used work energy, and we were happy with the results. But if I were one of you looking at this, I would feel, that this is quite artificial. Like, how is it that I can, just push something and put no rotation on it, and then all of a sudden something happens, and then it starts to rotate and fulfill this no slip condition. So what I want to show is what's happening, or what can cause this to happen. So essentially what I want to do is I want to look at the problem again, not from position 1 to position 2, but let's say from position 2 onwards. Let's call onwards a position 3 after, this wheel has moved for some time. So it's a kinetics problem. If I want to know let's say, if I want to know what happens after a few, meters of that disk rolling without slip on that surface, which of the kinetics tools do you think we should use? Do you still remember this problem? More or less? So just imagine that you have a disk that is rolling without slip. It starts to roll without slip, and you want to know what is its angular velocity after, or angular speed after 10 meters. What would be your first choice of kinetics to try to analyze that? Work energy. That's a sensible choice, right? And probably you can do it. Probably you can do it with work energy. But in fact, it's interesting to look at it from the angular impulse momentum point of view. So let's do that. So let me just show you the difference between when the disk is sleeping and when the disk is in the no-sleep condition to understand what's going on. So while we have sleeping, what's going on? We have this disk, it has, weight is acting there. We have the normal force acting there. And let's say that we have a friction force acting in this direction. Now, it is sleeping, so it's not rotating, right? Okay. So what happens? We need to say, okay, we need to do to use impulse momentum equations. This implies linear and angular, right? So for the linear momentum, we look at the forces in x, right? And then we see that we have friction force acting in the negative x direction, and then this is equals to the mass times acceleration. So of course that disk is decelerating as it's sliding, right? By the friction. Now if we look at the y direction, we have negative mg, positive normal force, and this is equals to 0, right? We have static equilibrium in the y direction, meaning that the forces are balanced. And if we have static equilibrium, what can we say about the linear momentum? Is conserved, right? And remember, conservation of quantities is very important. You're going to, now it may just seem a way to get some points in an exam, but as you start your practice, and if you remember, it's really going to be very, very useful when you can say that a quantity is conserved. Okay, so what do we learn from here? Just very similar to what we did with particles. That in one direction, because the forces are 0, momentum is conserved, linear momentum, and in the other one, we have forces, so we cannot really say that the momentum is being conserved. Now, let's look at the angular momentum for that part when we have sleeping. So for the angular momentum, we need to use the angular impulse momentum equation, right? Now, where can we take moments for the part where we have sleeping? About point C, I heard. About any other point? I see some. About the center of mass, right? Because it is sliding, it's sleeping. So point C is not really one of the good points that we talked about. Point C has a velocity. So here the only one that it's available is G, which is O, right? G or O are the same. So now we know that it needs to be G because our options were point C, but it is sleeping, so we cannot really take that one. And then mathematically, it's because C, the velocity of C is not 0. Okay, so we take moments about points G, and what we're going to see is the following. We're going to see that that if we take moments about point G, we get friction times R. Friction is to the left, to the right, so it gives a positive moment, is Ig omega. Now, what do we see from there? Nothing? Nobody is bothered by that result? Well, the angular momentum is not conserved, yes. It appears to be that it's not conserved.
So if it's like slipping through them with that index 13 before.
Exactly. So there is something that is, inconsistent there. There is some inconsistency in our assumptions, because we say that the angular velocity is 0, but this thing it has some friction. So there must be something that to get, if the angular velocity is 0 for some time, you need to have 0 angular acceleration. So there needs to be something that balances friction there. And there is nothing. But, okay, this is what would be a paradox. So this cannot really be physically. And paradoxes are not that the professor is wrong or the book is wrong, is that models have limits, right? And we need to be aware of these limits, because in the physical reality, if we don't model it, then we're going to get the wrong answer. So it's important to be aware of these paradoxes. And this is why I'm showing it here. So this motion cannot really happen if we have a friction force from position 1 to position 2. Or there needs to be an internal torque, some sort of engine that is precisely balancing this to keep it from rotating. Okay. Now, we can also see this in another way. We can also see this in this way. We can take that exactly when we're changing our model from sliding or sleeping to no sleep. This torque is the moment from friction is the one that is making our system rotate. Now, we go back to our paradoxical situation in which initially we have no angular velocity, and then in the end we have some angular velocity, right? I actually should say that it is over this very small period of time that we have this impulsive moment from friction, and that is the one that gives us the rotation when we change. But remember, now we're just seeing for a very small moment this impulse is acting. Before, due to a paradox, it cannot act, or there is something that is impeding this from happening, all right? But when we're changing from sleeping to no sleep, then that impulsive moment is the one that makes the wheel rotate. And then we see that, the friction since this guy is moving to the left, then its angular velocity needs to be counterclockwise, which is positive. So then this moment from friction needs to be positive, and hence our friction is going to be in the direction that we assume. So everything is working fine. All right, so let's see now what happens after position 2. So after position 2, our forces are still going to be the same. We have some friction, we have some weights, and we have some normal force. Now after position 2, we're told that this rolls without slipping, this disk. So we're going to use that model. What's the most important condition from rolling without slip? That the velocity of the contact point is 0, right? That's the big thing. So when we have that, now we can say, all right, that second term that I want to get rid of, it's working if I take moments about point C. So I can do that. And what we get when we have no slip is that this term, the impulsive part, the impulse, is 0. And we have conservation of momentums. Now, for this to happen, for having that impulse be 0, we need to have that our moments are 0, right? And that is working fine with this because we're taking moments about point C. There is no force that is causing any moment if we take moments about point C. And hence our momentum is conserved. Now, if you take your angular momentum about point G, is your momentum conserved? You have this friction. So you would have some impulse, and then things become complicated. This is why we need to take a judicious choice of the points that we use for calculating the angular momentum to avoid those complications. Okay, so here there is a mistake from the professor, which is this. This should be about point C, not about point G. Okay? So when we make things correct, then we can say that the momentum about angular momentum about point C is conserved, which means that we can say that right when we started the no slip condition and we have omega 2 value, at a later point, I can calculate my omega 3, after 10 meters, 14 meters, whatever, with using the momentum conservation. And what is this equation telling us? That omega 3 is going to be what? It's going to be the same as omega 2, right? Because our disk is not changing mass or anything in this case. So omega is constant when you are in the no slip condition. You remember what happens when we have no slip condition and the work from friction? It's 0, right? Thanks. So if that work is 0, then it makes sense that the angular speed is constant, right? Otherwise, it would be decelerated by friction. So friction is present, but it does not slow our disk. And then, of course, you're already telling and thinking, this cannot be Well, it is an idealized situation, of course, right? Of course, there is no way that without any source of energy, something can keep rolling with the same speed in perpetuum, right? That would violate our physical understanding of the world. But under the no-slip model, it is possible. Let's say the corollary of this, or the implications of this, is that the no-slip model works, but the condition in which we say that the relative speed between the surface and the point of contact is not physically correct. There is an area of contact and there is some sliding during that area, and that is what causes friction. But it's so small, if we look at it at a big scale, like what people say, or we say as a first order approximation, that it's not so big of a deal to take it and use it and calculate with it. All right. So this is a demonstration of. First, I illustrated how to calculate linear momentum for rigid bodies, angular momentum for rigid bodies, implications of the models that we use, right? And how they are connected and consistent with the models that we're using in this class with respect with work, energy, and the fact that if the momentum is conserved, then this disk is going to still go and rotate at a constant speed. Any questions about this? All right, so similar analysis is what you need to do in problem one for your homework for Wednesday. All right, so let's do this problem now to illustrate further how these equations work. It's a problem 5C5 on page 346. Okay, so in this problem we have a bullet that has some mass, mass m, and it strikes a stationary pendulum at a distance h from the pivot with some initial speed. So the bullet is carrying some initial speed, and it hits it at a distance h. Now the pendulum has mass m, capital M, and a radius of gyration ko, about that point O, the pivoting point. And then the bullet is embedded inside point A of the pendulum. So the pendulum has a radius of gyration. The bullet and the pendulum are, sticking together after the impact. And we were told that that pendulum was stationary in the beginning. And then we're asked to find the angular momentum, the angular speed of the pendulum right after impact. So we have impact, and we are asked to calculate the change of speeds. Which kinetics do we use? Impulse momentum. We may be tempted to use work energy, but remember that when there is a collision, energy is not conserved, and we don't know the work that is dissipated by the collision. So we need to use impulse momentum. Now, so we know that we need to use impulse momentum. Now, which one? Angular impulse momentum or linear impulse momentum? Angular, right? Because that pendulum is just under rotation. It's not really translating. There is no pure translation. So we use angular impulse momentum. So when we clarify those questions in our heads, we found the strategy to look into this, and it's because we have we have only rotation, and then we have a pivoting point about which we can calculate moments and get them to be zero. So if I add those forces there that I haven't added, sorry, and the weight, we observe that indeed moments about O are zero, right? There is no force with a moment arm. So we can, choose O in our angular impulse momentum equation. And that is a good choice because then we have zero here, right? And if we have zero in the moments, then the impulse part is zero. It's always useful. Nobody likes, like some people, but we don't want to calculate the integral. So we go to our definition of angular momentum for a rigid body. We call that h. But initially, this pendulum is not rotating. So there is no contribution from the pendulum in the initial state. The only contribution is from the momentum of the particle. Remember, the particle can have an angular momentum about a point. And that is calculated as the cross product between the distance of our particle to the point of rotation cross its linear momentum, m times v, right? Okay, so this is going to be, from the geometry, is minus h in the j direction cross minus vb initial or vb1 in the I direction. So we have negative, negative, that's positive, and j cross I is negative k. So we get the initial momentum is h m vb1 in the k direction. And remember, this is we only have angular momentum due to the bullet. But the k direction, of course, is out of the plane, right? That's right before impact, Now, after impact, that's our state 2. We're asked to find the angular velocity right after impact. So right after impact, this bullet is embedded. It has, initiated some movement. So the angular momentum in state 2 is going to be, we said that we're going to use point O for calculating the angular momentum. So the body now is rotating. It has this angular speed. And then we also need to remember that the bullet is embedded into the pendulum. So that bullet still carries some angular momentum, right? Now the good thing is that, so this is important. Don't forget that the bullet is embedded. The good thing is that we know that angular momentum is conserved, so we can use this to calculate what's going on. So initially we have this angular momentum in the system, h mvb1, bullet's velocity or bullet speed. And now this is going to be equals to this term here plus then, I forgot m here, sorry, plus the momentum of the particle, which is still the same, right? But it's just that the speed is different, so it's negative. And this is going to be our equation number 1. So we have one equation, but how many unknowns do we have? We have these and these. We have 2. We have the angular speed and the speed of the bullet after that pendulum starts to rotate. So we need to find more equations. So where do we find more equations? Why not work energy? Exactly. So sometimes you're going to have to combine work energy with angular impulse momentum equations. And next class I'm going to show examples of when do you do this. But in here, when we have a pure collision and we're told to find something right after the collision, we don't really have a way of using work energy because our second state is right after the collision. Right? We're comparing right before collision, right after the collision. There is no way we can use work energy because we don't have a model for the non-conservative work. So it's kinematics what we need to do. So the kinematics are rather simple. I hope it's rather simple by this time, right? Because what we need is to find a way to relate the velocity of the particle with the angular velocity of the pendulum. So we know that we have point O is fixed. So what is that? That's an instant center. Then here, I mean, just for completeness, our angular velocity is negative because it's clockwise. But we can just use instant centers to find that you know, the speed is negative also. Angular velocity is negative. So I'm just going, okay, let me just do this. All right. Or anyways, it's just negative. So it doesn't matter. I mean. So this is going to be my equation number 2. Now, if I substitute this into equation number 1, then I get initially I have negative h m b1, it's equals to IO omega 2. This is negative because omega 2 is negative. And here I have negative, I had already calculated this, H2 omega 2 H. So everything is negative. I can factorize that and make it positive. So I substituted these here, right? So we got then h squared. And then it's a matter of doing a little bit of algebra. I mean, we can just factorize, and we get that we have IO plus mh squared omega 2. That is the result we have. Notice that there is not like a parallax theorem or something in the calculation of this factor of omega 2. What we have is the fact that we have an additional mass to the pendulum. All right, it's important because we may have forgotten about that. And then yeah, now in the end it's just a matter of some algebra. We just send these to divide, and that's it. Well, the last thing is to remember the definition of the radius of gyration, right? It's just k o squared times capital M, and then as I mentioned, or as I wrote here, we keep our negative sign when we calculate the angular velocity. All right, are there any questions about this? It's, let's say, a more or less straightforward application of the equations. We remember what were the good choices for calculating the angular momentum, and then application of kinematics. Okay, I'm going to start here next class with the classical silly professor opening arms and closing arms. And then I'm going to, this is important, I'm going to send an email about exam 3, all right? So please read it carefully. Read it carefully, all right? I'll be sending that email through the afternoon. See you on Wednesday.